The second section of Unit 5 is verifying trigonometric identities. So it's taking what we did in the last section a bit further. We're not going to be using numbers anymore. So this is going to be more abstract for some people to understand. And the process has to be very methodical. So you're all very much able to do math, but trying to explain what you're doing is where some of you will find this a little bit more complicated. So what we're looking at is that there are going to be different ways to solve these trigonometric identities. We're going to use substitution, we're going to use factoring, we're going to use common denominators. And the process that I want you to do is I want you to work on one side of the equation only, and I'll model this in a second. You're going to have to draw a vertical dashed line through the equal sign to separate the two sides. Each step must be a valid mathematical step, and you need to write down what you're doing. My advice to you is if you make a mistake or you think you're doing something wrong, do not erase. Cross out your work and start again. If you erase, I can't see what your thought process was, but I need to see what you were thinking. If you're not sure, always start by just using substitution. And everyone in class could be coming to a different process, and you can all be correct. So please don't just copy off of somebody else is doing. Think for yourself. So the way I'm going to do this, I'm going to work through several examples. This first example I have is that cotangent x multiplied by sine x is equal to cosine x. So I'm giving you the answer. And this technique that I'm using is the most basic. You're just going to replace everything with sines and cosines. So I'm going to replace cotangent with cosine x over sine x. And the reason I can do this is because that is the reciprocal identity. My next step, I can multiply. When I'm multiplying a fraction, this is over 1. So cosine multiplied by sine divided by sine multiplied by 1. So my reason for this is I am multiplying. My next step is I'm replacing sine x over sine x with a 1. That's reducing that to get a 1. Some of you think of it as, well, if it's the same thing in the numerator and denominator, I'm canceling those out. So I end up with cosine x. And for me, cosine x multiplied by 1 is cosine x because I'm using the multiplicative identity property. And that's the last thing. So what you want to end up with, this last row right here, is going to be what you had wanted to get to. You can get to this in a different way. This is only one example. My next example is I have secant theta times cosine negative theta minus sine squared theta equals cosine squared theta. So in these processes, what I'm always keeping aware of is where I want to end up. It's like a destination. That's where I want to go. Since I want to end up with just something with cosines, I'm looking to change secant and sine squared. But my first step is that cosine negative theta is an even odd identity. We don't use them that often, and this year we're not focusing on them. But I can replace cosine negative theta with cosine theta. My next step is I'm going to replace secant theta with 1 over cosine theta. And I can do that because of the reciprocal identity. Then when I multiply, 1 over cosine theta times cosine theta will be cosine theta over cosine theta, which is 1. So all I did was multiply. I can replace this 1 with sine squared theta plus cosine squared theta using the Pythagorean identity. Remembering that I want to end up with something with cosine squared, so this is why I chose this, because it introduces cosine squared. Now I have a positive sine squared and a negative sine squared. That is equal to 0. So I'm left with just cosine squared. And when I add positive sine squared and a negative sine squared, I use the additive inverse property. You can say combine like terms. You can say adding, simplifying, however you want to. My next example is going to be using what are called the co-function identities. Once again, they're not very common. This year we won't focus on them as much. But I want to end up with a cotangent. So if I want to end up with a cotangent, I have to start thinking I want something with cosine over sine. So the first step is I'm going to replace sine pi over 2 minus x with cosine x. That's my co-function identity. Then I'm going to replace cosine pi over 2 minus x with sine x. That's again a co-function identity. Cosine x over sine x is cotangent x, and I use the quotient identity. So with what I started with, this is where I ended up, and each step along the way has a reason for it, a justification. Okay, this one gets more complicated. And the more you do these, the easier they get. We're not going to be spending a lot of time on them this year, but they do get easier. So this is something more complicated, and I want to get something simpler. So I've got a sine, and I have a cosine. So I want to get rid of this tangent and cotangent somehow. My first step is I'm going to replace this tangent with sine over cosine. And that's a quotient identity. When you divide by a fraction, you flip the fraction underneath and you multiply. So dividing by sine over cosine is going to be multiplying by cosine over sine. And I just put down that I'm dividing by a fraction. If I multiply these, sine in the numerator, this is sine theta over 1. Cosine theta over sine theta, the sine thetas cancel out, I'm left with cosine theta. So now I can go ahead and change this, cosine over cotangent. I'm changing cotangent to cosine over sine. Once again, just like my quotient identity from before. I'm going to flip the fraction underneath. So instead of cosine over sine, I'm multiplying by sine over cosine. My cosine over 1 times sine over cosine is 1. So I get cosine plus sine. If this were a proof, I would not be able to do it this simplistic. It would have to be a lot more involved. And I couldn't leave it like this. I would have to use the reflexive property and change it to sine theta over sine theta plus cosine theta. But this is good enough for what we're doing this year. The next problem I have, I'm going to use the technique of factoring. And you have to be very confident in factoring to be able to understand it with these problems. So I've got secant x minus secant x multiplied by sine squared x. And I want it to equal cosine x. So this is a lot more complicated to come down to something that is a lot less complicated. Secant x is common in both these, so I can factor my greatest common factor, which is secant x. And I'm left with 1 minus sine squared x. Remembering that I want to get down to cosine. My next step is I'm going to replace this 1 with sine squared x plus cosine squared x. That's the Pythagorean identity. Then if you'll notice, I've got a sine squared and a negative sine squared. Well, that's going to equal 0. So secant x times cosine squared x. I have the additive inverse property, or I simplified. Always keep in mind where you want to go. It's like playing chess. I want to get to cosine x. Well, I'm getting closer because I have a cosine squared x. So my next step is I replace secant x with 1 over cosine x. And I can do that because of the reciprocal identity. When I multiply these two, 1 times cosine squared x is cosine squared x. Cosine x times 1 is cosine x. So I multiplied them. And then I can reduce them. Cosine squared over cosine is just going to be cosine x. And that's where I get to the end. A few more examples. Actually, 2 more examples. And then I will do different examples during the live lesson. So I've got cosine to the 4th theta minus sine to the 4th theta. This is going to be factoring a difference of squares. If I had a squared minus b squared, it's a minus b, a plus b. If I have a to the 4th minus b to the 4th, it's a squared minus b squared, a squared plus b squared. So like I said, you have to be confident with your factoring. So I can factor this. Cosine squared theta minus sine squared theta is in one set of parentheses. Cosine squared theta plus sine squared theta in another set of parentheses. And I did go past my dashed line a little bit. So I factored a difference of squares. Then if you'll notice, sine squared theta plus cosine squared theta equals 1. So my next step is I'm going to replace this with 1 from the Pythagorean identity. And I'm not done yet. Always keep your eye where you want to go. I want to go to something with 1 minus 2 sine squared theta, so I have to get rid of this cosine squared theta. So I can do some manipulating of the Pythagorean identity. Sine squared plus cosine squared theta equals 1. If I were to subtract sine squared theta, I get cosine squared theta equals 1 minus sine squared theta. So I can replace this cosine squared theta with 1 minus sine squared theta. And that's using the Pythagorean identity. Now I can combine like terms. I have 2 of these, so 1 minus 2 sine squared theta is where I want to end up with, and I've combined like terms. And my final example for the notes. This technique I call common denominator. You're going to be given a fraction. Sine x over 1 plus cosine x plus 1 cosine x over sine x is equal to 2 cosecant x. So I'm going to get a common denominator. How I do that is I notice my least common denominator is going to be 1 plus cosine x multiplied by sine x. So if I multiply this 1 plus cosine x times sine x, I have to multiply the numerator and the denominator by that. Same thing on the second fraction. Sine x is in my denominator. I need a 1 plus cosine x, so I have to multiply both numerator and denominator by 1 plus cosine x. So when I multiply, sine x times sine x will give me sine squared x. 1 plus cosine x times 1 plus cosine x will be 1 plus cosine x squared. Don't make the mistake that a lot of people will make. Pay attention. If I have 1 plus cosine x squared, that means I have 1 plus cosine x multiplied by 1 plus cosine x. 1 times 1 is 1. Plus cosine x and a plus cosine x is going to give me 2 cosine x. Cosine x multiplied by cosine x will be cosine squared x. So that's where I'm going with the next step. The first fraction is the same. The second fraction I expand into 1 plus 2 cosine x plus cosine squared x. So I multiplied to get that. Now since I have the same denominator in both fractions, I can combine the numerator. Sine squared x plus 1 plus 2 cosine x plus cosine squared x. So all I did was add fractions. Then when I did, see this sine squared x plus cosine squared x? That's equal to 1. So that's where I get the 1 here. So I use the Pythagorean identity. 1 plus 2 cosine x is still there. I can combine like terms. I put this 1 plus 1 together, made it a 2. 2 plus 2 cosine x is the numerator. The denominator comes along. Don't forget to write your denominator. Then I had to go to another page to finish this out. I was able to factor out the 2 because it was the greatest common factor, and I had 1 plus cosine x in the numerator. Denominator still has sine x, 1 plus cosine x. 1 plus cosine x over 1 plus cosine x is 1. So I get 2 over sine x by reducing. And I think of this to show you I can break this fraction apart. I have 2 over 1 times 1 over sine x, make it easier for you to see. 1 over sine x is cosecant x, using my reciprocal identity, and so that is my answer.